to deliver the first report, effectiveness object detection for UAVs via control-based feature, extraction in compact neural networks. Thank you, Mr. Konstantin. Let's begin.
Good morning, dear colleagues. I'm not Mr. Konstantin, but today I will present this work.
Sorry.
Yeah. Good morning, my name is Alexey Zatsky, and I represent National Aerospace University, Kharkiv, Ukraine, Aircraft Control System Department. Today I will present our research paper made with Konstantin Dergachev and Konstantin Kulagin, titled Efficient Object Detection for UAVs via Contour-Based Feature Extraction and Compact Neural Networks. So this work addresses the critical challenge of balancing detection accuracy with computational efficiency on resource-constrained UAV platforms. As we know, UAV are widely used for navigation, monitoring, and other tasks. However, these platforms typically operate under strict constraints regarding processing power and energy consumption. The problem is that while modern deep learning models like YOLO and other offer excellent accuracy, they are often too computationally expensive for broad deployment. Therefore, there is a strong need to find a balance between real-time performance and acceptable accuracy on weak hardware. So the main goal of this research is to develop an object detection algorithm specially tailored for such resource-constrained platforms. So moving onto the methodology, we propose a hybrid detection pipeline developed within the Unity environment in the first stage and later transferred to the Python environment. As illustrated in a block diagram on the slide, the algorithm operates in few principal stages. So first is contour detection, where we use a classical image processing to find object contours. The second stage is contour analysis. Here we extract the geometric features. And finally, the third stage is class recognition. These extracted features are fed into a compact neural network to classify the object. So here is a detailed workflow of our contour detection stage. We pre-process the image using a Gaussian filter and morphological clothing to remove noise. Then, instead of just using one grayscale image, we split frame into blue, green, red, and grayscale channels. We apply adaptive binarization to each channel independently. We use a specialized micro neural network with a 2-4-2-1 architecture to dynamically calculate the optimal threshold value based on image contrast and brightness. Finally, we filter the contours based on their size and merge the results from all channels. This ensures we capture object or details that might be disappearing in a simple black and white conversion. So once contours is detected, we need to describe it numerically. As shown in the diagram, we extract a vector of 15 specific parameters for each object. The first 7 are hue moments. We calculate hue moments to handle rotation and scale changes, along with standard geometric properties like area, solidity, and other. So for the final classification stage, we employ a compact feed-forward neural network, as shown in the diagram. So the architecture is designed to be lightweight. It starts with an input of 15 neurons, which corresponds exactly to our extracted feature vector. This is followed by 2 hidden layers contained in 24 and 16 neurons respectively. Both use hyperbolic tangent activation function to capture nonlinear patterns. Finally, the output layers consist of 3 neurons using softmax. This gives us probability distribution for our three target classes. There was an airplane, car, and landing pad. So to objectively evaluate our algorithm, we benchmark it against three widely used detection models: YOLO version 5, YOLO version 8, and SSD MobileNet. We captured a real-world video sequence of landing pads, split them into individual frames, and manually annotated bounding boxes for every frames. So we measured performance using standard metrics based on true positive, false negative. Especially we calculated precision, recall, and F1 score. So we generate a specialized synthetic dataset using Unity engine and train all networks. On the right side, you can see the statistic graph of this dataset. We ensure a balanced distribution of classes and extensive randomization of environment parameters. And training results for YOLO version 8 and version 5, you can see on the other chart on the left side. Moving to comparative results, first let's look on the table on the right. This is the average processing time per frame on a standard CPU. While YOLO version 8 takes over 1 second, MobileNet takes about 60 milliseconds, our ContrastNet processes a frame in just 8 milliseconds. This makes it a great option for low power embedded systems without GPU. The graph on the left side shows the F1 score across the different intersection over union thresholds. You can see that MobileNet starts losing accuracy very early. Our method shows comparable results to YOLO up to thresholds near 0.85. But above this value, you can see a sharp drop in accuracy. This happens because contract-based bounding boxes are slightly less precise than regression-based boxes used in YOLO. But in our opinion, for standard detection task, this is more than sufficient. So in conclusion, first of all, I would like to note that this research served, as a baseline study to confirm the viability of our concept. At this stage, we believe we have successfully achieved our key objectives. We develop hybrid approach that effectively combines classical contour detection with lightweight neural network. As experiments demonstrated, our methods ensure significantly faster processing compared to resource-intensive models like YOLO or even MobileNet. Also, it maintains competitive performance at practical intersection over union thresholds. However, we acknowledge limitation. Accuracy drops sharply at very high thresholds, which is, is a necessary trade-off for such high speed. Regarding future work, we plan to increase the number of recognizable classes and sense complicity to enhance robustness. We also plan to optimize the algorithm for other resource-constrained devices. A critical next step is testing on real UAV hardware to validate our simulation results in real world. And finally, we see potential in adapting this hybrid framework to other computer vision tasks. This concludes my presentation. Thank you very much for your attention. I'm now happy to answer any questions you may have.
Sorry. Thank you for your presentation. It's very interesting and informative. Please, any questions? Are there any questions now? I have some questions. You tested the algorithm on the Intel i7 CPU. Have you tried running it on actual embedded hardware like a Raspberry Pi?
Thank you for your question. In this paper, we focus on comparative analysis on a standard CPU to establish baseline. However, since we achieve good results, we are confident that it will run in devices like Raspberry Pi, but porting and optimizing for these specific platforms is a part of our future works. Thanks.
Thanks. And I have a second one. The question, you trained your model purely on synthetic data from Unity. How well done it generalized in real-world scenarios? And did you observe a domain gap?
Yes, to address the domain gap, we use domain randomization, Unity, varying lighting, weather, camera angles, and other. But for validation, we did not just use synthetic data. We teach our models with this data, but we capture authentic video sequence of real landing paths and manually annotate them. So the results presented today confirm that the models generalized will, despite being trained on synthetic data, and will work on real data in the same way. Thank you.
Thank you.
Sorry, some connection error. We continue, sorry very much. We continue. Please, the second speaker is invited to take the presentation, Intelligent UV Autopilot with Terrain Guardians. Can we hear you?
Hello everyone, give me a sec, I will show a presentation. Okay, do you see my screen? I hope so, okay. Hello everyone, my name is Alexander Slesrenko, and I will have a pleasure to be here to represent National Aviation University of Kyiv. I'm presenting our work of Intelligent UAV Autopilot with Terrain Guidance, done together with my colleagues Dmitry Kucherov, Natalia Shnichenko, and Olga Sushenko. This research addresses a critical challenge in modern navigation when GPS signals are unavailable or potentially disrupted. Our approach combines terrain reference navigation with intelligent autopilot to achieve a reliable flight in GNCC denied environment, a problem of significant importance for both military and civil applications. So modern UAV are widely used for both civil and military purpose. However, their navigation system are largely depends on satellite signals, which may be unavailable or intentional disrupted. So this creates a critical need for autonomous solution. Consider several real-world scenarios. First is military operation when GPS in jumping is common. Civil aviation in mountains regions where GPS signal are unreliable, operation in poor visibility condition, and emergency situation where satellite infrastructure may be compromised. So this leads up to central question of our research: can we achieve autonomous navigation using terrain guidance and both sensor when GPS is unavailable. Recent advances show that position accuracy of 3 to 6 methods can be achieved in detailed conditions, matching or even surprising GPS performance in difficult environments. But our work builds on this advance to develop a practical intelligent autopilot system. Briefly position our work using the research worksheet. So for intelligence autopilot control, various approaches have been explored. Like physiologic control have shown success in marine and aerial application. Hybrid system combines multiple control strategy. Database learning methods enable real-time adaptation. Most recent, John and colleagues in 2024 demonstrate advanced path following for small fixed wings UAV under low altitude wind shape disturbance, showing the importance of robust control in challenging conditions. However, there remaining a gap is limited integration of terrain reference navigation when intelligent PID turning specific design for real terrain profile. In our work, addressing this gap by combining digital terrain map with machine learning based autopilot adaptation. Regarding system architecture, our system architecture builds on terrain approach, but with importance enhancement, as shown in Figure 1. The UAV on board computer combines altitude markets along file paths, coordinate information in consolidate from multiple source. First class is internal navigation system provides velocity and acceleration. Biometric altitude gives altitudes about sea level. The radar altimeter provides precise ground clearance, and the terrain height the database contains geographic elevation data. The key innovation is our use of digital terrain maps in standard format like GeoTIFF or KeyML. Based on missing start and endpoints, we conduct an elevation profiles of terrain. The road of then defined as smooth curve, maintaining a specific clearance height above the terrain. The mathematical foundation in our approach is straightforward but effective. Longitude motion with altitude control using the terrain transfer function. This represents the aircraft type UAV operation under long-range execution 10 kilometers. The autopilot use a PID controller with proportional, integral, and dividends gains. Our control objective is to minimize integral error. Next step is about intelligence autopilot structure. Provide flexible control through the machine learning and adaptation to flight condition. As we shown in Figure 2, the structure is multi-loop. The main loop uses position feedback, where epsilon equals the difference between desired and current position. The machine learning loop turns controller parameter for the current flight mode. The adaptation loop selects the approximate controller type. The PID controller can operate in 4 modes, for straight flights, contest altitude and speed. We use only a proportional component. For smooth maneuvers during the climb and landscape, we use proportional integral controller. For shape changes or atmosphere turbulence, we use proportional deviation controller. For complex maneuvers require critical accuracy, we use full PID controllers. Machine learning algorithm is the core of our intelligence steering approach. We represent the controller UAV system as state space equations. The machine learning algorithm change controller parameters so that the desired UAV position is achieved under variant environment condition. So the objective to find the optimal controller parameter that minimize a function representing position error. And slide number 8. Let me show that how we generate flight in rotor from digital terrain data. We use GeoT formats, terrain maps, which contain geographic metadata. The image is converted into file of geographic coordinates that use to conduct terrain profiles. And figure 3 shows a terrain profile from the under reach of Dnipro River. And figure 4 shows the middle section approximately 70 kilometers long. The blue curve here is representing actual terrain elevation, while the orange curve shows the smoothest UAV road trajectory, maintained to the average of clearance of 50 meters above the terrain. This demonstrates how our system generates safe, flyable roads that follow terrain contours while maintaining adequate abstract clearance. Now let's look at simulation results for different control type on 70 kilometers road. And table 1 shows accuracy metric. The full PID controllers achieve the best performance with RMCA of 4.9 meters. Maximum error is 14.6 meters and mean error 3.7 meters. The proportional controller alone show that RMCA of 19.6 meters for time worst. The PID and PD controller offer intermediate performance. And in table 2, we present time metrics. The PID controller achieves a faster settle time of 40 seconds compared to 82 seconds for the proportional controller. The maximum vertical speed command remains reasonable of 4 meters per second. A critical aspect of our system is performance in GPS-denied environment. Our simulation showed that rotor following incomplete GPS signal loss using only built-in sensor and terrain database achieve deviance not executed 50 meters, combined with RMCA of 50 meters ROS and 50 meters terrain clearance. This provides a 10-to-1 safety margin for obtained avoidance. Conclusions. Let me summarize the key contribution of our work. First, we develop in the integration terrain reference navigation and intelligent autopilot architecture. This combines digital terrain mapping with machine learning-based control terrain and adaptive mode selection, addressing the gap in what we found in literature review. And second, we achieve significant computation efficiency. Our approach requires only 10 iterations or fewer compared to 16 to 17 of traditional methods, making it suitable for onboarding real-time implementation with limited computing resources. And third, we demonstrate strong performance metric, accuracy of RMCA of 50 meters or better in GPS-denied condition, settle time of 30 seconds, road in following that less 55 meters deviation, and a 10-to-1 safety margin for obtained clearance. Thank you for your time. If you have any question, I will be glad to answer on them.
Thank you. Thank you. Please, if you have any questions.
Yes, I have
Okay.
question.
Yeah.
What types of terrain data are used in the system, and how is the relevance ensured during the real-time flights?
So if you understand the question, we use standard GeoTIFF maps For example, for our 70-kilometer test with 50 clearance, typing elevation data with 10 to 3 grids sufficient. So, could you repeat your second part of question, please?
Thank you.
Thank you.
The next question. How is navigation error accumulation handled during the long-term flights of the complex terrain?
Okay, regarding errors, it's our limitation. So our system relies on accuracy terrain data. However, radar altimeter provide real-time growth truth, so the sensor fusion can detect these errors. But for sure, for safety critical application, database verification and updates are essential.
Thank you.
Thank you. And I have one question, please. Do you investigate what challenges arise when operator UV with terrain guardians was in difficult environment, like at night or foggy conditions? It's only terrain.
Hard to say about
It's
it.
maybe in future, yeah?
Yeah, maybe in future, as well as using not only fixed wing. So
Terrain. Okay, I understand. Thank you. Thank you very much. And the next, moving on to the third report, automation of visual positioning of unmanned vehicle based on an adaptive cascade algorithms. Please. Thanks. Let's start.
Hello, can you see my screen? Can you hear me? Hello, welcome to the presentation, Automation of Visual Positioning of Unmanned Vehicles based on an adaptive cascade algorithm. Our team brings together specialists from the National Aerospace University, Harьків Aviation Institute, Harьків Aviation Institute and Azerbaijan Technical University, who works together to create innovative navigation methods. The main purpose is to develop a software architecture in Python for automated visual positioning of the UAV based on an adaptive cascade algorithm. The principle of operation of which is focused on modularity, reduced computational load, and intelligent adaptation in real time. In addition, a parallel direction of research is to assess the accuracy and performance of the proposed algorithm in real conditions, as well as analyze objects around UAV to determine the characteristics of its position using visual positioning methods. Methods that serve as a basis for creating an adaptive algorithm, proximity centroid, weighted centroid, and lateration. The logic of functional elements is implemented in a modular structure with iterative optimization of calculations, which allows for unhindered use of such a system on drones with limited capabilities. The proposed software has a three-level structure. The blocks of which are presented in the diagram on the left. The graphical user interface level contains widgets that allow the user to interact with the application. The application logic level contains functions responsible for the detections, analysis, and processing models of the received data, and the service level provides interaction between the system blocks in real time. The main options for modeling an autonomous system are presented in the diagram on the right side. The user can select display parameters when setting a detections range and apply visual navigation methods to video stream, view information on the dashboard in real time, and export the report to .txt format or Excel files. The following flowchart, which is presented on the slide, allows you to understand how the process flow in the software application occurs. Among the components are the launch and initialization of components, detection of objects, application of selected local navigation methods, measurements of their performance, export and update of the interface. The user doesn't have direct influence on the internal functions of the algorithms or commands for the computing core, since the system is able to work autonomously with any number of objects around and different sequences of their detection. Instead, the application of a certain visual navigation method is based on the condition of detecting a sufficient number of landmarks around the UAV and depends entirely on the user's choice. The images on the slide demonstrate the operation of the Auto UAV Navigator software application when performing two different tasks. In the first case, the image left objects are detected and their location is established using the visual navigation method selected by the user. The image on the right side displayed a pop-up interface window that works in parallel stream and displays the status on the video generation process in real time for simulation and experiment in a complex environment. Architectural decisions are made taking into account the requirements for performance, reliability, security, and the possibility of further expansion of the system. Thus, the principle of modularity of components was laid at the heart of the system development, which allows for unhindered scaling of the system in the future, as well as making it adaptive to changes in both environment conditions and tasks. The presented diagrams illustrate the structure of the system and the layering of components in their logical sequence from the moment of launch to the completion of the program execution. Among the presented components, calculation and processing functions, data arrays and dictionaries, as well as interface components that added to the system when they are directly needed. The line chart on the left shows the results of checking the accuracy of the methods in determining the current position of the quadricopter. As we can see, the determined position of the quadricopter calculated using centroid and proximity are quite close to the real position of the object in most cases. Unlike the previous ones, the calculation of the quadricopter position in space using the visual-oriented methods, weighted centroid and lateration, demonstrate higher accuracy rates due to weighting coefficients and solving the nonlinear system of equations by the least square methods. The bar chart on the right illustrates the distribution of error values obtained during the process of detecting various landmarks around the UAV using a color mask. The bars clearly demonstrate the variability of color recognition accuracy in the HSV space, allowing you to identify marginal deviations of marginal deviation, and as well as estimate the average level of error and at the stage of detection each object. To assess the performance of the developed software, the use of the main hardware resources of system was monitored. In particular, the central processing unit, CPU, and random access memory RAM. The pie charts show the shares of resources used by the program during the operation of each of the visual navigation methods. When using each visual positioning method for 30 seconds with the minimum number of landmarks required for its operation, it became known that the minimum value of RAM consumptions is for the use of the proximity method and is 160.5 megabytes and has an impact of the processor, which is estimated at 8.4%. Lateration has the maximum RAM reservation indicators, 252 megabytes, and the impact of the processor of is 28.7%. In both cases, the value of a moderate load on the processor cores in the context of determining the current position of the quadrocopter DJI Tello EDU in the local environment is the normal. Okay. Therefore, the proposed software application Auto UAV Navigator, which provides automation of the local positioning progress based on cascade algorithm, is an important contribution to the research, as it allows not only to detect objects and calculate their position based on the basic methods of visual positioning, but also choose the most accurate one of them, as well as to conduct modeling in complex environments. Among the future direction in the context of this research, the following can be noted: that development of methods for compensation and error correction using statistical models or machine learning, integration of additional sensors data, in inertial measurement units or data from the depth cameras, scaling experiments to more complex environment, including dynamic scene, external opticals, and changing light conditions. This concludes the presentation of the research results. Thank you very much for your attention and interest in this research.
Thank you. Thank you for your informative presentation. Please, if you have any questions. If there are not questions, allow me to ask. Slide 3 show a diagram. What are the graphics and the computer cores responsible for in a use case modeling system?
Thank you for your question. When the program is executed, commands are received from the user. This can be both pre-processing of the image and changing the display of the frame or applying additional information to the image, which is associated with the process of the video adapter. The graphic core is responsible for the execution of this process. The computational core is responsible for a network of process associated with algorithms for detection and determining the parameters of landmarks in space, as well as a method for UAV orientation. Each stage of calculation is accompanied by recording data and corresponding arrays for further comparison and export. Calculation process occurs inside both cores, graphic and calculation cores, and differ the speed, approaches, and areas of its application.
Thanks. Thank you. Thank you, Mr. Alexey. And the next one, we have the fourth report. Tatiana Khavarushenko is invited to speak. Adaptive Guardian System for Unmanned Aerial Vehicles.
Good morning, dear colleagues. Tatiana Khavarushenko is in another section right now.
Okay.
I will be reporting today.
Thank you.
I am happy to present my research on the topic Adaptive Guidance System for UAV. In this work, we explore new approaches for precise UAV navigation control in the presence of external disturbances, such as strong winds. Traditional methods often fail to provide the required accuracy and stability, which is why we turn to cutting-edge technologies, artificial intelligence, and adaptive controllers. The main objective of our research is to develop an adaptive UAV guidance system that used artificial intelligence method to change position accuracy. A key component of this system is the integration of horizontal thruster, which allow for precise position without the need to change the UAV's orientation. Additionally, we implement a recurrent self-evolving fuzzy neural network that adapts to change in the environment and disturbances. To achieve precise UAV position during the guidance phase, we applied a two-loop control strategy. The first loop is responsible for stabilization, orientation, and altitude, while the second loop ensures precise adjustment in the horizontal plane to estimate disturbances and uncertainties in the UAV's dynamic. We developed a recurrent self-evolving fuzzy neural network. It accounts for the temporal dynamics of disturbances and adapts to change in input signal. Testing of our system showed a significant improvement in position accuracy, especially in conditions with strong wind disturbances. The use of horizontal thruster minimizes energy consumption during maneuvers, since there is no need for constant orientation adjustment of the UAV. Additionally, adaptive learning through RSEFNN helps reduce errors and improves performance under uncertain conditions. The developed UAV guidance system provides high positioning accuracy, even in the presence of intense disturbances such as strong winds. The integration of horizontal thrusters and recurrent self-evolving fuzzy neural networks significantly change energy efficiency and adaptability of the system. Future research will focus on improving adaptive learning algorithm for even greater accuracy. Thank you for your attention.
Thank you. Please, if you have some questions.
I have a question. What estimates of robustness did you use in your work? Estimates of robustness.
Thank you for your questions. I understand the questions, but I am afraid I might not formulate the answer precise enough in English. Sorry.
Okay, we try again, please.
You say about improving robustness as a result of your research. And I ask what types of estimates of this robustness can be done. Robustness
I'm so sorry. It's difficult for me to answer in English.
Okay. It's no problem. Have you any question?
Now, I have question. What stability guarantees are provided when adaptation occurs during the flight?
We say that we say that stability UAVs can be very well because we I'm sorry.
Next question. What computational resources are required for real-time adaptation on board of UAV? You understand question?
Stop so. I am sorry, I'm not answered to your questions.
Thank you.
Okay. To my mind, maybe we can stop the question for our speaker. And can we go to the fifth report? Mr. Stepan Simchenko is invited to deliver the fifth report, Adaptive Reliability Modeling of UV Swarms using Binary State System and Multi-State Systems under Uncertainty.
Sorry, wait a minute. I just
Okay.
changed my setting on a browser, and I will start
Okay.
my presentation after 5 minutes. Okay, or I may miss my position and пропустить вперед. Ну, человек.
Okay. Okay.
Я 2 хвилинки, типа, в мене тут з комп'ютером якась лажа.
Okay, we understand. And next we listen sixth report. And after that we are listening you. Okay, we have some changes in our list. And now we can listen a presentation, Influence of Partial Communication and Influence of partial communication and sensor factors on the evaluation of unmanned ground vehicle complex application effectiveness. Good afternoon, dear colleagues. Your attention is invited to a report of the topic in the slide. I represented the Hetman Petro Sakhaidachin National Army Academy, Lviv, Ukraine. Our academy is conducting research in evaluation of the UGV usage effectiveness. Now I will present you the results of some of our research. Today, there is a rapid development and mass application of unmanned system in various spheres of human activity. Unmanned ground vehicles are being developed and implementation for various needs, logistic, engineering support, evacuation, etc. Samples of any types depend on maneuverability, autonomy of operation, and especially high-quality communication. A platform with high cross-country ability and maneuverability, convention and high-quality equipment, manipulators, gear, etc., become vulnerable and immobile upon loss of communication. Analysis of recent publication demonstrated a significant percentage of UGV control and communication loss due to the influence of electronic warfare (EV) in the active jamming zone, up to 30%. The main factors causing problems in the C2 system, command and control, should be divided into two corresponding categories. The first category covers the difficulties arising in the operation of communication means, and the second category covers sensor composition. There are several ways to improve and modernize the C2 systems, communication channel redundancy. For example, mesh plus UAV relay plus Starlink plus fish ESS, etc. Sensor fusion as a basic architecture. New or improved communication components usually require additional energy consumption, which is depend on specific implementation. For example, Starlink mean peak 20 to 16 watts or more upon connection establishment in stable mode for 10 to 30%. Typically, each 20 to 40 watts is approximately 1/2 to 2% of the energy budget per 1 hour. It reduced operation time. Therefore, it is important to investigate the contribution of C2 systems improvement to the overall evaluation of UGV application effectiveness, considering the additional battery energy consumption of the UGV required to ensure the operation. Static indicators for determining the evaluation of UGV application effectiveness is carried out using the analysis hierarchy method with the following four main group criteria: functionality, maneuverability, reliability, autonomy. UGV functional properties are determined by the ability of perform tasks as intended, transport, evaluation, recognize, surveillance, etc. The list and the naming of these indicators are determined by the ability to perform task as intended, transport, evacuation, and depending for this aim. For UGV application effectiveness evaluation, the weightless sum method was used. It is happened improvement of one or more sub-criteria values during platform modernization. The sensitivity analysis is used to evaluate the influence of these improvements on the overall effectiveness indicators in the platform. The authors previously conducted research on evaluation the effectiveness of UGV application. It was found that the net increase in effectiveness was 2%, but the energy cost, the modifier party parameters, reduced the effectiveness by 1.34%. Within the framework of this work, attention is focused in verify the influence of modify the communication components in the UGV's power supply and the overall effectiveness rating of its application. The analysis of factors affecting the energy consumption of the C2 system occurs through the values of the instantaneous power of the involved factors, subsystems, and mechanism. It was investigated the energy expenditure permission. It is depend to the instantaneous power in time interval. Share of expenditure for C2 functioning, communication plus computer for C2 in percentage. For testing within the research, the main subsystems and mechanism on which the ground platforms is battery energy is spent and outlined. Motors, sensors, computer, communication, and actual systems. They check the influence of increase in communication load on duration of the mission or autonomic operation time, and the experience was conducted for a typical ground platform of two classes, small and medium UGV. The ground complex are designed to perform monitoring, surveillance, and additional logistic tasks. The experiment was conducted using 4 scenarios. Scenario 1, baseline. Typical activity locomotion consumption for an average vehicle UGV. It was the same for always scenario. Basic communication equipment of the C2 systems, and we have drive energy consumption dominates. The influence of communication on UGV operating time is present but not critical. Scenario number 2, modified. Typical movement and the individual components of the C2 system are improved. For example, Starlink mesh models are additionally installed. And we have P motors dominated, and the load of communication increase. Scenario 3, modify high load. High load on the improved components of the C2 system, for example, streaming HD video. And we have active consumed for motors load. There is a significant increase in communication load and an additional load of computation. Scenario number 4, counteraction to EV. Streaming HD video mission under EV influence. Counteraction to EV means active consumption motors load, load of communication increase due to increase in the number of retransmission, increase the transmitter power, and so on, and an increase in computer load, data preposition and compression, encoding, decoding, etc. Initial assumption: average value of output powers in watts were taken for the considered 1 hour interval, peak operation period of 1 minute to 10 minutes. Normal instantaneous power are typically estimated values for small medium class platform taken from open resources and technical reviews. Analysis of modeling results show that the active counteraction against EV means lead to a substantial increase in energy consumption, but for both UGV types. An increase in the application effectiveness of the modeling sample relative to the baseline is observed 72 to and 53% for both UGV classes, while counteraction against EV mean reduce the effectiveness rating by 20% for small UGVs and 16% for medium UGVs class. Figure number 1 and 4 in the next slide The corresponding 3D diagrams scenario 4 EV influence jamming effect was chosen as an illustrated example. We take scenario 3 modifier high load as the initial state. And now jamming is applied. Communication load to potentially increase from 2 to 5 times, depending on attack intensity. We assume the 3-fold increase. Additional cost of decoding and protection increase, computer load, we show. The share of energy of communication increased from 17% to 36%, more than 2 times. It's shown in Fig 2. The total energy expenditure per hour increased by approximately 16%. This sharply reduced the mission time from 2.5 to 1.7 hours shown in Figure 1, which is a 28% reduction. Similar for the medium UGV. The share of energy of communication increased from 8 to 20%, almost 2.5 times, showing Figure 4. The total energy expenditure per hour increased by approximately 20%. This sharply reduced the mission time from 4.9 to 4 hours shown in Figure 3, which is a 16% reduction. So, now in conclusion, it has been proven that active counteraction against EV means lead to a significant increase in energy consumption depending on the scenario for both classes of UGVs. In this time means reduce the effectiveness rating by 20% for small UGVs and 16% for medium UGVs. The second one, in numerical examples with a 3-fold increase in communication load, the mission duration can be reduced by approximately 16% for medium UGVs and 78% for small UGVs. It was being shown that improving communication components directly affects UGV power consumption, increase it. The energy costs of C2 can be small in simple transit mode, but during intensive reconnaissance or under EV attacks, it's increased significantly. However, with competent design and the application of energy effectiveness solution, its maybe cost can be reduced this. Thank you for your attention. Any question? Any questions?
Questions. Did you conduct research on a single model, single sample, in the relevant UGV class, small and medium, or were options for group use considered?
Okay, thanks. Our report is part of a comprehensive study. We evaluated the effectiveness of using the UGV unit for various tasks. For individual application, we tested the impact of specific partial indication, like precision, load capacity, protecting, in particular the C2 system communication and components. We conducted research on the effectiveness of using a group of similar samples of various functional tasks in different missions. The C2 systems impact was investigated for single UGVs usage only. Thank you.
Thank you for your report and answer.
Is any questions? Oh, okay. That I can go to our fifth presentation, and we try again. Mr. Stepan Simchenko is invited with a report, adaptive reliability modeling of UV swarms using binary state system and multi-state system under uncertainty.
Hello, do you hear me? Do you see me?
Okay.
Hello, do you hear me?
Okay.
Yeah.
We see you and we listen you.
Okay, nice. Hello, dear colleagues. My name is Stepan. Today I will present research on adaptive reliability modeling of UAV swarms using binary states and multi-state system under uncertainty. Let's begin with relevance of the problems. Modern unmanned aerial vehicle is increasingly operate not in individual but as swarm collectives of dozens or even hundreds of autonomous agents interacting with each other. However, serious challenges arise. First, under electronic warfare condition or GNSS signal loss control system experience failure leading to degradation of individual agents and or even complete mission fail. Second, traditional reliability models operate in binary logic. A system either works or fails. But for UAV swarms, such simplified logic is insufficient. For example, a drone may lose connection to the central node while retaining local navigation function and the ability to interact with neighboring agents. Therefore, the key question arises how to ensure swarm survivability under partial agent failures, how to maintain system functionality when it's neither fully operational nor complete failed. To solve this problem, we propose an integrated methodology combining two approaches, binary state systems and multi-state systems. Our approach consists of two sequential phases. Phase 1, mission planning. Here we use the binary state systems model basis. At this stage, we need to determine the optimal number of agents in the swarm considering operation environment uncertainty. For decision making under uncertainty, we applied two classical criteria, the Laplace and the Hurwitz criterion. We consider three realistic operation scenarios. First, nominal condition where individual agents reliability is 0.90. Second, moderate electronic interference, reliability drops to 0.09 or 0.082, and third, strong GNSS jamming, reliability falls to 0.72. The result of this phase is optimal K out of N configuration, guaranteeing the specified system reliability level. Phase 2, mission execution. Here's a multi-state system models. MSS separates each agent can exist not only in working or failed states, but also in intermediate degradation states. We use multi-factor effectiveness evaluation considering 5K indicators: average agent reliability, algebraic connectivity of the communication graphs, average communication range, communication cost, and local autonomy level. Based on this evaluation, the system can automatically adapt its topology in response to degradation. And this is a key advantage of approach. Instead of catastrophic failure, we achieved graceful degradation, smooth functionally reduction. Now let's look at concrete results from the first phase, phase planning. We based our analysis on a minimum or mean equal to 4 operational agents. This means that for successful mission completion, at least 4 fully functional UAVs are needed. The question is how many total agents should be included in the swarm to ensure system reliability. We tested different configuration. With 5 agents, system reliability range from 0.57 to 0.92, depending on the scenario. In the worst case, strong jamming scenario, this is an insufficient robust configuration. With 6 agents, situation improves to a range of 0.74 to 0.97, but still remain risky. This 7 agent system reliability exceed 0.90 in all 3 scenarios. With 8 agents, reliability increased by only 2%, while cost increased significantly. Both decision criteria, Laplace and Hurwitz, give a consistent result. The optimal configuration is 7 agents with a minimum of 4, ensuring system reliability above 0.95. This is a perfect balance between reliability and economic efficiency. We don't waste extra resource, nor do we risk mission failure. Moving to the second phase, topology, selection and its adaptation during the mission. We examined 3 classical communication network architectures for swarm, stars, tree, and mesh. Now let's look at multi-state system analysis results. We evaluated each topology effectiveness using our multi-factor utility function U. The higher the value, the better the topology for given conduction by Laplace correction. On screen by Laplace it's 0.37, 3.49, and mesh 0.55. By Hurwitz creation, results are nearly identical. The conclusion is ambiguous. Both criteria recommended decentralized topology mesh as the optimal starting configuration for the mission. Why mesh? It provides the highest algebraic community of the graph, about 0.44 to 0.58, and high local agent autonomy level about 0.90. Even in the worst case scenario with strong GNSS jamming, it maintains effectiveness at 0.52. And now most interesting part, what happens when the system is attracted during mission execution. Imagine a real scenario. A swarm of 7 UAV is performing a large territory monitoring mission, and suddenly the adversary activates a powerful GNSS jammer. Well, what happened to our agents? Agent on 1 South 3 are at the edge of coverage area. The complete loose navigation and connection enter emergency landing mode. Their state is 0, complete failure. Agent 4 South 6 were closer to center, and the time of attack they retain peer-to-peer communication and continue navigation using inertial measure units with accuracy of ±50 meters. Their state is 2 interoperability. The 7 agents is the only one remaining in the backup GPS transmitter zone or has a protected receiver. It can serve as anchor for relative navigation of other. Its state is 3 full operability. So the system state configuration becomes 00223. Only 57% of agents remain at least partially operation. What does the classical binary model say? It says system failed because we have fewer than 4 fully functional agents remaining. But what does the multi-states model show? We calculate effectiveness for different topologies in this degraded state. Star shows effectiveness of 0.25, 3.35, and mesh near 0.4. Above our critical threshold of 0.38, the adaptation rules triggers if an alternative topology provides effectiveness gain greater than 0.04, while remaining above the critical threshold with switch. And the system automatically, without operator intervention, transition to decentralized structure. Compensation for not loss executively through communication graph reconfiguration. Key result: with 43% agent loss, we retain 40% of system functionality. This is not catastrophe, this is graceful degradation. The mission can continue perhaps with reduced effectiveness, but without complete failure. This is critical, important for autonomous operation beyond line of sight, where humans cannot quickly intervene. It's my conclusion and contribution. We receive a concrete partial result. We determined the optimal configuration. It's 7 agent with a minimum requirement of 4 ensure system reliability above 95%. Second, we demonstrated the graceful degradation effect. The system retained 40% functionality even with 43% agent loss. And third, all the adaptation occurs autonomously without operator intervention, which is critical for mission in challenging conditions. In my future work, we see 3 main development directions. First, it's a transition from discrete statistics scenario to stochastic dynamic models. It's a Markov decision processor. Second, integrated with machine learning. And third, develop of distributed optimization algorithm for scaling to large swarms with more than 20 agents. Thank you for your attention. Please give your question.
Okay, thanks.
Sorry, but a little bit rush my presentation.
No, it was very informative, very interesting. Thank you.
But I feel a little bit bad in my condition. Like, sorry for.
It's good. Thank you. Any question, please?
I have question.
Okay.
Which operational scenario shows the highest sensitivity of the models to uncertainty levels?
Please repeat your question without because I don't understand what do you mean sensitivity.
Uncertainty.
Uncertain. Please repeat your question, please.
Which operational scenarios show the highest sensitivity of the model to uncertainty levels?
It's scenario in EV condition, in electronic warfare condition. If I understand your question.
You use your system in different scenarios.
Yes, it's scenario without any problems in area and moderate EV condition and hard EV condition. It's spoofing, jamming, or another another problem in air environment.
Which scenario shows the highest sensitivity?
It's scenario with harder EV condition. In our work, we show you a result in 3 scenario: in moderate, in easy, moderate, and harder. And based on research in all of them, we give you result среднестатистическое.
Average.
Average. Its methodology can support operator operate a swarm of UAV in each of them scenario, of 3 scenario. I explain you. Perhaps we use our swarm. We start our swarm in easy condition, and in process of flight, our EV environment is harder, and we calculate for this method how it's a second method, multi-state system, how our system will be complete our flight. Understand?
Yes.
And it's all. And your question for sensitivity, of course, sensitivity was чувствительно in harder EV condition. Understand? But harder EV conditions provide problem with all of system UAV. It's IMU, it's autopilot, it's barometer, it's airspeed, and all system in autopilot and second primary system of UAV. Understand?
Thank you.
Okay. Thank you. It was very interesting dispute. we listen. Thank you very much.
But problem it's dispute that I don't nice handle with English, and I don't understand, and I don't explain that I mean on Ukrainian, and it's may, це може здати, що я типу не дуже гарно поясню, але якщо ви мені задасте там українською мовою, то я вам повністю розкажу, що я маю на увазі.
Okay. We understand that you now your theme, you're interesting and you acknowledge, and you have some problems with English. And with
Little bit, in technical and professional segment.
Okay. It was very interesting. It was very good, nice. Thank you. Thank you, colleagues. We listened for reports. Thank you for your attention. We have heard all reports of our sessions. This conducts the work of our sessions number 7.1 is complete. It was informative and interesting work. Thank you for all your reports, for all your questions, for your attention again. Thank you all for your productive work, and have a nice day, and see you again soon. Thank you. Bye.
Thank you.
Have a nice day.
Nice day.